Okay, so here's what we were doing last time. Talking about this thing called a directional derivative, represented by this notation right here. What is a directional derivative? Well, it's based on the idea of this interpretation of the chain rule. We have this interpretation of the chain rule that says that you can interpret the gradient vector in the case of, real valued functions. Right? The gradient vector is a relationship between input velocities and output velocities. Right? So if you give me some input velocity in the domain, or an input vector of any sort representing maybe a differential, maybe a velocity, then dot product with the gradient gives you the corresponding output vector. Again, could be a velocity, could be a differential. So the gradient is the relationship between input velocities and output velocities. Okay, input changes and output changes. Okay, so the idea is to say, well, okay, let's consider the special case where the input velocity is a unit vector. And the idea, again, just as a reminder, we call this a directional derivative because we use unit vectors to represent directions. And you can see the root right there, right? Direction in the term directional derivative. And there are certain advantages to doing this. We started talking about this last time, didn't finish. So anyway, picking up from there, I was beginning to make this case of how it is that the directional derivative has an interpretation that's very natural in that it is what you might want to call df/ds. How fast is the function changing, not per unit time, but per unit distance traveled in whatever direction you're going. Right? And now, let me try to make the case for why this is something you should be interested in. Now, why the directional derivative computes this, separate question. We'll get to that in a minute. But why should we be interested in df/ds? Well, for example, maybe I'm driving along a road, right? And I'm interested in how fast the temperature is changing as I drive along the road, right? Well, I personally might be interested in my own personal experience of how many degrees per unit time is the temperature increasing, right? But that's me personally, right? Someone driving faster is going to get a larger value. Someone who's driving slower is going to have a smaller value. It makes a lot of sense to talk about, at that moment, given where you are on that particular road, what's the rate of change per unit distance traveled? Of course, people who are going faster, you're going to have a higher scalar. People who are going slower are going to have a lower scalar. But as far as the road itself is concerned, how does temperature vary along the road? Independent of your personal observations, based on your experience. In terms of temperature changing as it moves along the road, this is what you should be interested in, right? Rate of change, number of degrees per mile traveled, not per minute as you drive. Okay, all right, so why is it then that the directional derivative computes this? It's a really easy argument to make. Let me remind you that velocities can be interpreted as derivatives, dx dt. Right? Further remind you that all vectors can be thought of as a direction and a magnitude, and in the case of velocity, that magnitude is speed. So our velocity vector we're going to break down as a product, like so. Unit vector times a speed. I'm going to take that equation and do something with it. Here's that equation again, same equation. What I'm going to do, I'm going to take this equation and I'm going to dot both sides with the gradient of f, just to see what happens. It's going to turn out that something very convenient, nice interpretation happens here. So dotting with that gradient, as you see, let's make sense out of what has come out. Over here on the left side, gradient of f dot v. Oh, that's df dt. That's the chain rule. We knew this from the very start of the lecture, or you might say we talked about this in the section on the chain rule. df dt is computed as gradient dot velocity. What is this v here? That v, this scalar, that's speed. Speed is distance per unit time. You might call that ds dt, right? They're literally distance ds per unit time dt. Okay, and with those observations having been made, knowing that this is that and that's that, this remaining object in this equation, which, by the way, is the definition of directional derivative. I mean, just look at this is a situation where the single variable chain rule kicks in. This then has to be df ds. That makes sense to everybody? Yeah.
Would this be considered like an application of a partial derivative, or is this like a separate?
In some sense, everything we're going to do involving derivatives is kind of an application of partial derivatives, because everything involved, I mean, this gradient vector here is made up entirely out of partial derivatives, for one thing, right? So in some sense, everything's an application of partial derivatives, but that's I don't think that's a point of view that we need to worry about right now. But I think it is. Yeah, sure, absolutely. Okay, so directional derivative is df ds, as we were hoping. All right. Here's another interpretation of directional derivative, and this is very convenient sometimes. You can view that directional derivative. Keep in mind, right? This is a special thing. That's a unit vector. Using a unit vector in the definition of directional derivative, what you get, this directional derivative, is the slope of the graph of that function. And I urge you, resist the temptation to say that it's the slope of the function. We have to distinguish between the function and the graph of the function. You can get away with that little crime in Calc 1 classes, because in Calc 1 classes, every picture you ever draw of a function, of course it's a graph. What else would it be? There is no other picture, right? So the distinction is not a big deal. Not so here, right? In this course, we're going to be looking at graphs of functions, level sets of functions, etc. Right? So specifically, if you want to interpret directional derivative as a slope, it is specifically a slope of the graph of that function. And not further specifically in the direction of that unit vector. Right? So if here we have a function of two variables, real valued function of two variables. You want to know how f changes as a function of distance traveled in the domain. There's our domain, the x1, x2 plane. As I'm moving in this direction, the slope of the graph is pretty clearly the rise, df, over the run. Let's see, color choices. I'll use this blue here. The run, the distance traveled in the direction I'm going, that's ds. That slope is pretty clearly df ds, which we just got through agreeing is the directional derivative. Right? So this directional derivative is df ds, which is the slope. So that's kind of nice. Sometimes you're looking at graphs of functions. Sometimes you want to know what the slope of that graph is as you move in a certain direction in the domain. If so, the directional derivative is the thing that answers that question for you. Okay. Here's some computational examples. And I like this metaphor of thinking of functions of several variables as representing temperature. I find it relatable, right? Hard to think of something that you have a visceral experience in that can be thought of as a function of location in 3 space, right? Temperature, I think, is a pretty good one. Yep. So I use this one a lot. And suppose you're moving along a curve parameterized by a given parameterization, like so. How would you compute, as you move along that curve, dTds, and I emphasize, there's a temptation to look at this and think, a little bit too casually and think, derivative of the temperature function. Derivative means rate of change. That means I want to know how fast it's changing, and to inadvertently conflate this with dt dt, which is not the same thing. Okay, we want dTds. Well, good news. dTds, we already know, is computed by the directional derivative. Right? So independent of how fast I'm moving, if I want to know along my path what's the rate of change of temperature with respect, per unit distance traveled, to give something that's absolutely intrinsic to the picture of what's going on with temperature as it relates to this curve, independent of my own travels, my own personal experience. dTdS is that thing. The directional derivative computes it. We have a formula for how to compute that. And note, of course, this does have to be the unit vector pointing in the direction that we're going. That's how you compute a unit vector in the direction of a given non-unit vector. Right? Our velocity indicates, the direction we're going, but you've got to divide by the magnitude to make that a unit vector. And straight-up computation at this point. Okay. Now, let me not oversell this particular example. Sure, we do avoid having to reparameterize in terms of S. I mean, that's a little bit inconvenient, finding the arc length function and, rewriting, reparameterizing, a little bit annoying. But of course, here's another alternative way I could have done this. I could have written this as dt dt divided by df dt. Right. Once we restrict our attention to along a single curve, everything in sight's a single variable function. Temperature is a function of distance. Distance is a function of time. Single variable calculus will do this, and both of these things are easily computed. In fact, that, you might say coincidentally, is that, and this is that. So you see you're going to get the same answer. Right. So, okay, arguably not the best example in the world for directional derivatives. Here's another one. Suppose this time we actually do want to compute dt dt, right, the rate of change of temperature with respect to time. And we're given an actual velocity vector, like so. Right? Well, I could, I suppose, use chain rule. Chain rule crushes this. The chain rule gives an explicit formula for doing this. I can take the gradient of the t vector, gradient vector of the t function, dot it with my velocity vector, and that will give you the correct answer. It's perfectly fine. Chain rule crushes this. I will point out, though, nice observation to be made. This thing that we are trying to compute, I could rewrite it with the single variable chain rule, like that, and then notice that conveniently dTdS is a directional derivative, which is a partial derivative, because my unit vector is a standard basis vector. Oh, we got lucky on this one, right? Sometimes the unit vector is not a less convenient thing to work with. The temptation to say, look, the way you make a unit vector is you got to divide by a magnitude, which means you have to compute a magnitude, which means you have to deal with square roots. Right? Sometimes the unit vector pointing in a given direction is less convenient to deal with. This time it's more convenient. Lucky break. And directional derivatives in the direction of standard basis vectors are just plain old good old partial derivatives. The rest of this, of course, is easy to deal with. This ds dt is just the speed, which is clearly 2.7. Right, so we didn't have to compute the whole gradient. All we had to compute is this one partial derivative. So it's a little bit of a time saver sometimes. And that's kind of nice. Okay, these are just examples. And by the way, before I go to the next thing, let me point out, I hope that you are not terribly persuaded by these examples. I think there is a problem that I've noticed in how a lot of students approach these ideas, which is to overinterpret the benefits of the directional derivative. These examples being a little, sort of boring and unimpressive, help me make this point, which is that directional derivatives are not always something that will make your life easier, right? They're just a different thing. Directional derivatives compared to the chain rule, they have different interpretations. The chain rule computes for you, you might say, depending on how you apply it, df dt. Directional derivatives compute df/ds. Neither one's better. They're just different. Sometimes one is easier to compute. Sometimes the other is easier to compute. So, so again, there's this temptation for students to sort of assume, and not unreasonably, but to assume that, look, material that comes later in the course must be an improvement, a more powerful, replacement. This is version 3.0. What we learned earlier in the course was version 2.0. Who would ever use the earlier version when the late version is out and accessible, right? So some people just reflexively take every derivative question and say, okay, I got to figure out how to use directional derivatives to answer this question because, of course, it is better. It's just not true. So I like this example here a lot. Suppose you have some velocity vector given and you want to compute derivative with respect to time. This is nothing weird at all. This is very real world. Sometimes you're moving with a velocity. Sometimes you care about your own personal experience of how temperature is changing with respect to time for you. This is all very reasonable. Let me show you two different ways to answer this question. One is you could kind of force it and try to cram this into using the directional derivative. And here's how you'd use the directional derivative. The directional derivative, of course, is dt ds. I want to compute dt dt. dt dt relates to dt ds by the single variable chain rule. That directional derivative, of course, you can compute in the usual way. Don't forget, your velocity has to be a unit vector in order to use directional derivatives, right? Your ds dt, of course, is speed, which is the magnitude of the velocity vector. So that's a calculation that you could do. We rewrote this problem in such a way as to use our brand new, shiny directional derivative. Okay, look at the alternative, though, just using the chain rule. The chain rule says if you want to compute dt dt, cool. Dot with the gradient vector. Bam, done. It's much more natural in this case. In fact, you can almost kind of make fun of this solution involving the directional derivative, because what have we done? What's the difference between these two calculations here? The difference is, in this upper calculation, I had to compute the magnitude of the velocity vector. That's a calculation. I then had to divide by that magnitude and then subsequently multiply back by that exact same magnitude, right? So what a ridiculous bit of effort there. This is pointless compared to, look what's left over. Bad color choice. What's left over here after that silly cancellation is exactly what the chain rule would have directly taken us to. Okay, so anyway, I emphasize, don't just throw away the chain rule and reflexively do everything with directional derivatives. That's a huge mistake. It's conceptually naive. Right? Understand that the directional derivative is different. It's got different interpretations. Sometimes it's what you're looking for. Sometimes it's not what you're looking for. It's got different computational perks. Sometimes it's more convenient. Sometimes it's less convenient. They're just different. Okay. So it's important to understand the distinction and the relationships, and then apply appropriately and compute cleverly. Okay. All right. All righty. This is a great time to bring up a related topic. We're going to talk about gradient vectors. Now, we've already talked about gradient vectors before. Again, it's a computational convenience. It's a bookkeeping convenience. It's a notational shorthand, you might say. It's what you get when you take the Jacobian matrix of a real valued function and kind of, sort of turn it sideways, make it vertical instead of horizontal, make a vector out of it. It's a vector made up of a bunch of partial derivatives. We've had a very algebraic point of view on the gradient up to now. So now I want to show you some neat geometric interpretations of the gradient. There are some really nice ones. I remind you, we're talking about real valued functions here. So functions that have a single output value. And here is a very reasonable question that one might ask about such a function. Given some starting point location, of all unit vector directions from that point, which one maximizes the directional derivative? Now let me try to give you an example of why we would care about such a thing. Suppose that I'm out in the woods and I'm super cold, but I have somehow or another, I don't know, I'm just making this up. Somehow or another, I know the function f that tells me temperature as a function of location on the map. Right? So I know this function that describes my temperature. I'm cold. I want this temperature to increase as fast as possible. Right? So which direction do I run? Right? Shivering. Which direction do I run to make the temperature increase as quick as possible? Now, this, I think, is a good opportunity for me to explain why we would restrict our attention to unit vectors. Because if someone were to tell me while I am out in the woods, cold, trying to figure out which way to run to increase, to get warm as soon as possible, if someone were to tell me, run faster, right? Yeah, I know. I am cold. You don't have to tell me to run faster. I'm running as fast as I can. I just don't want to be running in a silly direction, right? So I'll handle the me running as fast as possible part, right? And let's talk about the related question of course I'm running as fast as possible. Which direction should I run as fast as possible? Yeah? Everybody on board? Okay. Okay, so how do we resolve which of these unit vectors points in the direction that makes my my directional derivative as high as possible? All right. So here's the way we answer this question. This directional derivative, I have a formula for it. If I want to make that directional derivative as high as possible, I want to make that dot product as high as possible. Reminder, here's how you compute dot products. So I want to make that as high as possible. For all of these different vectors, I want to make this expression here as high as possible. Well, here's another thing. The magnitude of that unit vector is clearly 1, which is constant. Right, so I can scratch that term off, that factor. Here's the other thing. The magnitude of the gradient. Look, I'm at this point. That's where I am. Right, the gradient vector, which is, I don't know, something like this. There's that gradient vector. That gradient is always the same at that point. It doesn't matter if I'm from that point running north, or from that point running east, or from that point running south, southeast, whatever. Right? The gradient of f, gray. That gradient is independent of what direction I'm running, because I'm evaluating at A specifically. So if I want to make this function as big as possible, this is what I need to maximize. I need to make cosine theta as big as possible. The angle between the two vectors. So this angle here, right? That's my theta. I need to make the cosine of that angle as big as possible, and that's an easy trig problem. Right? You just have to think back to, your memory of trig functions. By the way, just while we're here, quick reminder: trig is very much in the prerequisite trail of this course. Right? Calc 2, Calc 1, prerequisites for those are, all of high school math. So if you are a little rusty with your trig, it's not just you. A lot of students come into Math 212. It's like, oh my gosh, that was like a year and a half ago. Long time. Maybe you've forgotten, kind of a little rusty on your trig. You definitely need to brush that up. This course will assume that you are rock solid with trig. So make sure that that's the case. Again, if it's not, find some resources. There's of course a million resources online. Get a good book, whatever. Make sure that you're really good with trig. Okay. So yeah, you want to maximize the directional derivative? We need to maximize cosine theta. That's easy. It's done when theta is equal to 0. Whoops. Theta is equal to 0. And by the way, when theta is equal to 0, keep in mind theta is that angle. Theta equals 0 means that I want the unit vector that points in the same direction as the gradient. So this is our picture. If that's the gradient, the unit vector that points in that same direction, easy formula by the way, the unit vector pointing in that direction, that is the one that, didn't want to do that, that's the one that makes the angle theta equal to 0, thus maximizes cosine theta, thus maximizes the directional derivative. Is everybody on board? So by the way, this makes the gradient, I'm going to call it conceptually natural. Right? Previously, the gradient was a notational convenience. If you were to take all the partial derivatives and assemble them to make a vector like this, then check it out. We can just say dot product instead of writing down a bunch of terms in the chain rule. It was a notational convenience. It was a shorthand. Now it's natural. It's always pointing in the direction that you should run when you're cold. You know, take your preferred metaphor. Everybody on board? Yep.
So, like, pointing in the same direction, does that mean, like, over a shorter amount of distance, it will change the greatest amount?
Yeah, it means, so by saying that this is the right unit vector, right, so this is the answer to the above question, what we're saying is that the gradient is always pointing in the direction that will make the function increase as fast as possible. Or said differently, the unit vector that points in the direction of fastest increase, we call it, that unit vector is the unit vector pointing in the direction of the gradient. Yeah. Okay. Okay. Now, again, here's our scenario. Right? I'm cold. I'm out in the woods. Which direction do I run? Now I know the answer to that question. I know what direction to run. Now, as I'm running, I might reasonably be thinking to myself, hey, how fast am I going to be getting warmer here? You know, per kilometer that I run, how many degrees do I get to enjoy? How many degrees of warmth? And I know how fast I'm running, right? I can, you know, deal. But I would like to know every distance that I travel, how much benefit do I get? How fast? What is the rate of change of this function with respect to distance, right? So that's a really natural thing to want to talk about, df/ds. So what's the answer to that question? Well, good news, df/ds, we already know is the directional derivative. We already know that the directional derivative is computed with that formula. We have just argued on the previous page that the ideal unit vector, the direction I am running, shivering, is that one. Gradient of f divided by the magnitude of gradient of f. And so I can answer my question of what is df/ds in that direction with that expression, which, by the way, don't forget that dot product with the gradient is magnitude squared. So I have magnitude squared divided by magnitude, which is magnitude. Right? So the answer to the question of how much, what is the rate of change in that direction, the magnitude of the gradient. This is actually also, this is another argument for why the gradient's a natural thing. Its direction, we have previously seen, is the direction the function's increasing the fastest. I like to call it the direction of fastest increase. Its magnitude is another natural thing. Its magnitude is what is the rate of change in that direction. So I think this is a nice way to characterize the gradient then. This is not just a notational shorthand. This is a really natural point of view. The gradient is a vector whose direction is the direction of fastest increase and whose magnitude is the corresponding rate of change. Very natural. All right. Now let me go back to the original question here, and I want to make a different interpretation. That's a very, very different interpretation from what I made before. Same question here. maximizing the directional derivative. Let's suppose that instead of looking at the function this way, let's suppose that I was looking at a graph. So maybe instead of which way do I go to make my temperature increasing as fast as possible, maybe I'd like to know, okay, I'm on a hillside, and I would like to know which direction should I go to ascend as fast as possible. I want my height. I want to think of the function as representing height. So increasing the function as fast as possible means increasing altitude as fast as possible. It means I want to run uphill. I'm climbing this mountain, want to get it done as quickly as possible, something like that. So which way do you run to go uphill? Which way is uphill? This next question, df/ds, thinking of the function as representing height, keep in mind the directional derivative, aka df/ds, we've interpreted that a few pages back. That represents slope of the graph. Right? So keeping that point of view in mind, let's go back to this little summary we have of the gradient. Different interpretation. The direction is uphill. Right? It's the direction of what we call steepest ascent, which is just a fancy way of saying it points uphill. Right? And its magnitude, df/ds, is, well, again, in the context of a graph, it's the slope of that graph. Right? So be aware. So, by the way, these two different terms, the direction of fastest increase, the direction of steepest ascent, both of these terms are out there. Both of these terms are reasonably natural in their different ways. You're going to hear a lot of people talk about the direction of steepest ascent. The little asterisk that I will put on that, and this is just for your sort of interpretation purposes, when you hear people think direction of steepest ascent, you have to remind yourself, oh, okay, they want to think about this function from the point of view of the graph of this function. And when they say steepest ascent, they're saying which is making the height increase as fast as possible. Oh yeah, they're thinking about graphs, so height means the value of the function. So keep that in mind, right? That terminology, steepest ascent, makes sense only in a single context of the graph. So, it's fine, I suppose, but I like to point out, what if you're not? What if you're not thinking about a graph? What if there is no graph to draw because it's four-dimensional? In that context, it doesn't really make any sense to say direction of steepest ascent. That's just downright confusing. So I encourage you to use the term direction of fastest increase. I think it's a better term. It's more broadly reasonable. But be aware, culturally, you're also going to hear direction of steepest ascent. Okay. All right, so those are nice interpretations. One final interpretation of gradient. This is a really neat fact, very useful. We're going to see a use of this momentarily. Whoops, there we go. Gradient vectors are always perpendicular to level sets of that function. That is a remarkably unexpected, weirdly true fact, that they're always perpendicular to level sets. And I emphasize level sets, not graphs, right? Gradients aren't perpendicular to parametric curves or something like that, right? Gradients are perpendicular to level sets, specifically and only. So again, I know I say this a lot, but you got to make sure to be ultra clear in your mind of what does that word level set mean. Always interpret it precisely with respect to that terminology, and only with a precise interpretation of level sets can you accurately interpret what this statement is saying. Did I see a hand somewhere? No? Okay. All right. Okay, so just as a reminder, when we say perpendicular to level sets, we are talking about a function f. The output values are, let's see here, I'll do this in red. The output values are, real valued. Got some target over there. And the domain that we're looking at, Rn, this is where level sets live. Right? So level sets live inside the domain. The gradient lives inside of the domain. The gradient's going to be it's going to turn out to be something like that. Right? But so this statement, gradients are perpendicular to level sets. This statement takes place in the domain of this function f. This function f right here. Anyway, just make sure to keep the context in mind. Okay, now how do I know this statement is true? How do I know that gradients really do look like that and they're perpendicular to this level set? So being a level set, reminder, being a level set, we're looking at where the function is equal to a constant. And let's just think then about some tangent vectors. Here's the tangent plane at that point. You can imagine that tangent plane. Let's suppose you have some little differential vectors here, little displacements from the point at which you're looking at the tangent plane. Here's the thing. If you're moving along the tangent plane, then you're moving with the surface, because that's what a tangent plane is. Right? So all of these little dx vectors have the feature that you're moving along the along the surface. The surface has f as a constant, and so along all of these tangent vectors, df is equal to 0. First observation, right? As you're moving parallel to a level set, by definition of level set, the function's at that instant not changing. Level set means function's constant. Okay. So what do we do with that? df equals 0. Well, here's where easy place to go with that. We have a formula for how to compute df. df is computed by that dot product. So if df is equal to 0, what we're saying is this dot product is equal to 0, and I'm running out of colors, aren't I? Oh man, I really am running out of colors. If a dot product is equal to 0, that means that we have a perpendicularity. And let me just get rid of the colors have gotten to be a mess here, so let me get rid of all this stuff. If df is 0, then these dx vectors, all of these tangent vectors, tangent to the surface, all of those tangent vectors are perpendicular to the gradient. That means the gradient is perpendicular to everything tangent to the surface. That means the gradient is, you might say, perpendicular to the surface. So it's a pretty straightforward argument. Very nice little result. Let me show you how you can use this neat fact. We've already talked about the tangent plane. You know how to compute the tangent plane to a graph of a function. So this is way back. This was in 13.4. Right? We made an argument about partial derivatives, and we derived the equation of the tangent plane. Here's a different way to get there. This is a reproduction of a known fact, right? So it's not new ground, but this is a really nice interpretation. Suppose you're looking at a graph of some function. Now I emphasize graph. All right, that's what it means to take a graph. You're taking the function of two variables and setting its output equal to a new third variable. Okay. All right, that's what we mean by a graph. You remember this little move we pulled where you can always reinterpret a graph as a level set? See here, level set, because we're setting this new function called g equal to a constant. So this function g has level sets that are the same as the graph of this function f. So I hope you remember this little trick we pulled. This was in our discussion of the sort of the first couple of sections. 13.2, I guess it was. So we spent a bunch of time talking about the difference between graphs and level sets. Okay, so, and I even mentioned, I think at the time, that sometimes you're given a graph and it's convenient to reinterpret it as a level set. This is one of those times. So what was given to me as a graph, I'm now thinking, I don't want to think of it as a graph. I want to think about it as a level set of this other function. And from that point of view, thinking of it as a level set and using the fact on the previous page, gradients are perpendicular to the surface, and therefore I can think of as being a normal vector to the tangent plane. Right? So this is really nice, right? Here I have on this previous page, and the way I described this some time ago was, you know, there is such a thing as calculus of level sets, and then there's a very different calculus of graphs, right? The calculus of graphs gives some interpretations of, you know, partial derivatives or, you know, slopes of cross sections and stuff like that. Here's some calculus of level sets. Gradients are perpendicular to those level sets specifically, right? We have no such theorem in the context of graphs. Gradients aren't perpendicular to graphs. Gradients are perpendicular to level sets. So knowing gradients are perpendicular to level sets allows me to instantly write down a formula for the normal vector of the tangent plane that I'm looking for. I can choose to be the gradient of this new function g that I created, the function whose level set is the original graph I was interested in. Okay, and it's all over with the shouting. If you know the normal vector, that normal vector goes into the equation of a plane, like so, and you can move the terms around like this if you like. There's that normal vector. We know our tangent plane goes through this point, x naught. You can kind of see sort of right here, if you will. And multiply it out, toss terms around, and bam, here's your equation for your tangent plane. And you'll probably recognize this. This is the equation of the tangent plane that we wrote down a long time ago, back in 13.4. So, very nice point of view. It comes straight out of reinterpreting a graph as a level set, identifying that new function appropriately, and then pulling the trigger on this powerful property about gradients, relationships to level sets. Understanding the calculus of level sets. Okay, neat fact. I think it's a nice application. Okay, let's see here. We have 7 minutes almost left. Okay, so new chapter. We're moving on now to chapter 14. Oh, by the way, just a reminder, you may have noticed, and I sent in the email, that we skipped 13.5. Right? It's an optimization thing. We're going to come back to that later in the course. Likewise, we are just now skipping 13.9 and 13.10 momentarily. We will come back to those sections later in the course, at the very end of the course. But for strategic reasons, I like to move them to later, so we're skipping them for the moment. So don't do the exercises for 13.9, 13.10 yet. Wouldn't make any sense. It's not going to come up till much later. Okay. So I want to remind you all about some things about integrals, single variable integrals, and I know you're thinking, I got an A in that class. Calc 2, crushed it, right? And you might, though, be sketchy on some important foundational points about integrals. And I know you're probably really good at cranking out integrals, right? And all the, doing the substitutions and trig substitutions and integration by parts, all that business. But I want to ask, by definition, what is an integral? And let me give you a series of wrong answers. Of course, I have the right answer on the screen here, so that, this is not I'm not actually going to ask. This is all rhetorical. A lot of people think integrals are antiderivatives. Very importantly, no. Very importantly, that's not the definition of an integral. And it would be very problematic if that were the definition of an integral. I'll explain why in a moment. So then students say, oh, of course, I know, antiderivatives are functions. Okay, so integrals are, we have this formula f of b minus f of a. Does everybody remember that one? Capital F of b minus capital F of a? A lot of students think that's the definition of an integral. Every integral I've ever computed, that's the first thing you write down. Surely that's the definition. No. Very, very importantly, not true. That's a true fact about integrals under certain conditions, which are usually, I'll say. But that's not the definition. The definition, very importantly, is a different thing. Okay, next wrong answer students very often give. Okay, integrals are defined as the area under the curve. Okay, area under the graph. Okay, area under the graph if the function's positive. Let's shorten that to the area under the curve. This is also importantly wrong. The area under the curve is not the definition of an integral. It is the by far most common picture that is drawn to represent integrals. Every picture you've ever seen, I imagine, the vast majority of the pictures you've ever seen to represent integrals are pictures of areas under curves, and I know this. But it is very important to understand that is not the definition of an integral. Here it is. The definition of an integral is that it is a Riemann sum. An example of which is this right here. Now, why am I making a big deal out of this? There is a temptation to say that, this is just, uptight mathematician, right? If you're interested in the purity of, the rigor or something, then you have to write stuff like this down. But, a working, useful knowledge of integrals, that this is all completely irrelevant. Who does this? Nobody does this, right? They made me do this once or twice. The very first time I was, right at the beginning of the calculus class, and they make you write this down, and then they show you the fundamental theorem of calculus, and you never go back, ever. Who would do this? Right? It's not the point. I claim that this, digesting that this is the definition of an integral is of extreme application benefit. It's very important. If you want to do anything with integrals, it's extremely important to understand that integrals are Riemann sums. So let me show you why. Here are various applications that you're going to want to do. You probably already have done applications of integrals. How do you compute the amount of work that it takes to lift a chain that's hanging off the side of a building up to the top, right? Population of bacteria in a petri dish, or the amount of volume of a surface of rotation, or there's just application after application. There's lots and lots of different applications. Calculus books are chock full of various different applications of integrals, most of which have nothing to do with the area under the curve. Area under what curve? Right? So, for example, let's suppose you wanted to take a work question. I want to compute the amount of work that it takes to pull a chain up the side of a building. What curve? What physics formulas do you know that directly relate work to area? I claim none. Right? Work is force times distance. Force is not an area. Right? It's just not. Right? So the way that you address a work application, let me just go ahead and get into highlighter mode if I'm going to do that. The way you address a work application is you argue that, look, as you pull the chain up, little pieces of work are force times distance, and then you've got to add that up over all the little incremental bits of progress that you make as you pull the chain up, and this as a summation, of course, with a finite number of tugs will have a certain amount of round-off error, and so you take the limit in order to make sure that computes correctly. And in that argument, where we're talking about chain hanging off a building with forces and distances, there's nothing in that argument that in any way relates to area, as argued. Area is not relevant to that, right? But we are directly relating the application to the Riemann sum. We have done that immediately, right? And I'll confess that, the area, area under the curve, that's one of the applications over here, and that's nice, I suppose, right? But it's got nothing to do with this work application. Now, so you say, right, but here's the thing, in thinking about this work application, I have to write down this thing, but I can think of, as I'm writing down force times distance gives me work, I can think of force as, let's look at the graph of the force function, and if I think of force as height, and if I think of distance as the x-axis, then when I write down force times distance, then I can think of that as a rectangle. So you can force it. You can choose, if you really want to involve area in that argument where you're using the Riemann sum to compute work, but you are not doing this. That does not make any sense. Right? You are not directly relating work to area. You're choosing to pointlessly think of area in what is, in fact, really ideally an immediate application of work to the Riemann sum. Okay, so I think my larger point stands, and that is when you're doing an application, right? Very importantly, applications go by taking the application and writing it as a Riemann sum. That's why we care about integrals. We define integrals to be Riemann sums because Riemann sums are the things that take this tremendous number of applications and allows us to get our hands on it mathematically. And then, yes, by the way, of course, I am very aware that then the fundamental theorem of calculus, that whole formula involving f of b minus f of a, that helps us turn the Riemann sums that we've just written down into number answers that we need. Yeah, for sure, right? But the Riemann sum is the essential. That is the node on this diagram that connects everything together. Riemann sums. Okay, so make sure. So I'm out of time. Make sure to keep this in mind. By the way, if you're a little shaky on this point, let this sink in. We're going to spend a lot of time talking about integrals as Riemann sums, and that's going to be essential to how we generalize this into the coming contexts. Okay, see y'all later.